Hello, everybody. This is the video for chapter 20, and in particular, we'll be focusing a lot on sections 20.4 to 20.5. So you're responsible for these sections. One formula from 20.3 that we'll go over. It's on something called the root mean square speed of gas molecules. And yeah, so a lot of this is just talking. It's a little bit more theory about where these values of CV come from. So we're going to talk in some generality. Just as a warning, a lot of students really have a trouble with this section, these sections in particular. So really, if you're not understanding the video, please seek out help on Piazza. Okay, so the question we want to be able to answer here is, suppose we have a mixture of two different kinds of molecules. So 1 mole of oxygen molecules, and then in addition, 1 mole of helium. And they come into equilibrium, which means that their temperatures become equal. So I have in mind thermal equilibrium. And we're asked a couple questions. Which molecule is moving faster? So by this I mean, so whether you have O2 or you have a single molecule of helium, the molecule itself is moving translationally. So we mean translational. Movement. We're not taking into account any rotational movement. Okay, so even though this thing might be rotating, which we're going to talk more about in this video, we just mean like the speed of the center of mass of that molecule, and we don't have to worry about the distinction for helium, right? It can only move. And then, as we'll see, oxygen actually carries more of the thermal energy in this mixture. And it's not the fact that it's because oxygen is heavier. So even if this was lighter than this element right here, it would still be the case that the oxygen had more of the thermal energy. So we'll have to talk a little bit about that. Okay, so to understand this section, we need to first go over something that I'm going to reference a lot, and this is called degrees of freedom. Degrees of freedom. So what a degree of freedom is it's a independent way of storing energy. So what we mean by this is how many different ways. We'll have to be a lot more specific about this, but I just want to give you a general idea here first. How many different ways are there of storing energy in your particle, in your molecule? And the best way to talk more about this is to give two particular examples for exactly these two kinds of cases, the diatomic molecule and the monoatomic. So for a monoatomic, there are 3 dimensions of translational motion. So this molecule, because it can move in the x, y, and z directions totally separately, we say that this has 3 translational degrees of freedom. DOF for degrees of freedom. In addition to this, a single atom like this cannot rotate or vibrate. So you think of maybe a solid sphere as something that could rotate around itself, but really this is like infinitesimally small. At the size of atoms, a nucleus is infinitesimally small, and there's no rotational energy associated with just a monoatomic atom. So in addition to this, there's no rotation or vibration here. Which is going to be different for the case of oxygen. So a monoatomic gas always has 3 degrees of freedom, no matter what. So monoatomic has F equals 3. So we're defining degrees of freedom to be this quantity F. Now your book doesn't introduce this thing F, but it's nice to have something referring to the number of degrees of freedom. So I'll just call it F. Some other textbooks use F. So monatomic means F equals 3, always. For oxygen, or in general for any diatomic molecule, this always has 3 translational degrees of freedom. So same as helium. And if anything, it could have more. So in addition to this, a diatomic molecule can rotate. So there are 2 rotational degrees of freedom. And the reason for this is that, this molecule can rotate around this axis. So you can imagine this thing on the left is coming out of the page and this one on the right is going into the page. So that's rotation around that axis. Another thing is that this thing could rotate about an axis that's going into the page. So it can also rotate around this axis, which corresponds to it rotating in the plane. Right? So if this thing on the left is going down and this thing is going up. You might ask, well, why can't it rotate around this axis, around its own axis? That's sort of the same question as why can't a atom rotate around itself? So if these are point-like things, that moment of inertia is 0. So really there's no energy required for that motion. And for that reason, we don't consider that a degree of freedom. Remember, these things are ways of storing energy. So if it requires no energy to rotate around this axis, because these atoms are indistinguishable, undergoing that kind of rotation, then that's not a way of storing energy. So these diatomic molecules can rotate, or they can have. So hold on. Let me finish this thought. 2 rotational degrees of freedom. I'll just put maybe. And so more on that in just a second. And then also there are 2 vibrational degrees of freedom. Maybe. So this is a little harder to visualize. So really the way this comes about has to do with upper division physics. And really it's how many quadratic terms are we adding to this function that keeps track of total energy called the Hamiltonian, or a related thing called the Lagrangian. We don't have to worry about that here, but really the reason that where this 2 comes from is remember in vibrational motion, in simple harmonic motion, half of the energy is kinetic, half of it's potential. So, and there are two different terms in the total energy, one associated with each of those, 1/2 kx squared and 1/2 mv squared. So if the molecule is vibrating, so you have to imagine like a spring connecting the 2 atoms for oxygen. So if these are going back and forth, the vibrational degrees of freedom are accessible. So the key thing here is that it depends on the temperature. On the temperature, whether these degrees of freedom are accessible. And this is where quantum mechanics actually comes into play for the first time. So you're used to having, so if we just focus on like this picture right here, you're used to being able to rotate something however slowly you want, right? You could rotate this infinitesimally slowly. So this could be going very, very, very slowly, and this going up very, very, very slowly. It turns out in quantum mechanics that that's not true. So just like the energies are quantized from like the Bohr model, you might remember from chemistry, it's also true that the energy associated in this rotation is quantized. So you could not be rotating, or all of a sudden you're rotating at some certain speed. But there's a minimum energy jump. There's a quantized energy jump. And you can't just go arbitrarily low in energy here. Now the energy required to get this thing to start rotating, you might say, well, is the thermal energy is like are the neighbors of this molecule. So suppose you have a diatomic molecule here that's going, if it knocks into it, is that enough energy to get this thing to rotate? And that depends on the temperature. And that's exactly why it depends on the temperature whether these degrees of freedom are accessible. And in general, at room temperature, diatomic molecules are rotating but not vibrating. So at room temperature, O2 is rotating. So in its collisions with nearest neighbors, that's enough energy to get it to rotate. So it can store energy in the rotation, but it's not vibrating. Okay, so later on, we'll come right back to the equipartition theorem, but I want to look at this graph right here. And this graph is exactly saying at what temperature these degrees of freedom become accessible. So this is temperature, and in this graph on the left, they're plotting CV. I'm just going to talk about degrees of freedom, F. So you have 3 degrees of freedom for a while, for a lot of temperatures. And then you'll notice that there's a jump here at around 100 Kelvin. So the order of magnitude here is about 100, couple hundred Kelvin. It jumps up to 5. So the number of degrees of freedom would be 5. And room temperature would be about right here. So F equals 5. And then at around 1,000 Kelvin or so, or tens of thousands of Kelvin, we jump up to 7 degrees of freedom. So up here is 7. So what this corresponds to is this is the molecule just translating, just moving in space, but it can't rotate or it can't vibrate. Here, this is rotation plus translation. So of course it can move in 3 dimensions here, but then also it can rotate. So here it's just translational energy. Here it's translational kinetic energy and rotational kinetic energy. And here it's all 3. Here it's translating, it's rotating, and it's able to vibrate. Okay. So why do we care about this? Numbers of degrees of freedom. So in summary so far, there are 3 degrees of freedom for monoatomic always, no matter the temperature. And then for diatomic, the degrees of freedom is 3, 5, or 7, depending on what temperature it is. Now the reason we care about this is something called the equipartition theorem. Okay. Equipartition theorem. And in summary, what this is for every degree of freedom accessible to a gas, there is 1/2 kT of energy per molecule. So per molecule, per degree of freedom, there's 1/2 kT of thermal energy. Should probably insert the word thermal. Okay, this is an extremely powerful statement. And this will allow us to look at this, to derive these values of CV that we had in the previous video. Okay, so the total thermal energy then, so just based on this equipartition theorem, the total thermal energy is due to all the molecules. So there are n molecules, and for each molecule, how much thermal energy does it have? Well, it has 1/2 kT energy per molecule for every degree of freedom. So we also have to multiply by the number of degrees of freedom. So that's the total thermal energy. So we can rewrite this as N, so we'll write F over 2, capital N kT. And remember, capital N times K is lowercase n for moles times the ideal gas constant. So we have thermal energy is equal to F over 2 nRT. And that's, so right here, the first equation that your book says is E thermal is 3/2 nRT for a monoatomic gas. So you can see that this is just a special case of our more general result, that the thermal energy is F over 2 nRT, and they just went ahead and plugged in F equals 3 for a monoatomic gas. But you can see how general this result on the right is. So if we go down to where a diatomic gas is, so solids is a different story. for a number of accessible degrees of freedom. For diatomic molecules, see right here, E thermal energy is 5 halves nRT. So they plugged in F equals 5 for that one. And the reason they did that was they're considering room temperature, where we're in this region right here. So your book always assumes that diatomic molecules are at room temperature. You know, they're assuming that you always have temperatures around 300 Kelvin or so. And that's why they went ahead and plugged in F equals 5. So really in any problem that I give you, I'll have to tell you, so if I tell you at your room temperature, you can assume F equals 5 for a diatomic, or I might tell you which modes are accessible. So I might say a diatomic molecule is rotating and vibrating, and it's up to you to determine that F equals 7 in that case. Okay. So also, so we want to compare this with an equation that we had from 19.7. So remember I said that the section is related to 19.7. So we want to compare with also delta E thermal is NCV delta T. Remember that equation from 19, this is from 19.7. So if we look at these two equations right here, so I can derive this second equation from the first one by just taking the differential of both sides, or just take a delta of both sides. And so we can see there then, in comparing these two, that CV is equal to F over 2 R. And therefore CP, which is CV plus R, looks like that's F plus 2 over 2 times R. I wouldn't bother memorizing this. It's more important that you know this relationship, and then this is the simple one to remember right here. So CV, the molar heat capacity at constant volume, is related to the number of degrees of freedom. So see how this is, the degrees of freedom is related to how much energy you're packing in at a certain temperature. And that's because the molecule is storing energy not only in moving around, but maybe in rotating and maybe in vibrating. So it's just ways by which the molecule can store energy. Okay, thermal interactions and heat. So actually I want to mention one thing about, so the relevant piece of the previous section. So what we need from 20.3. So no matter what, so whether you have monoatomic or diatomic, no matter what, the translational kinetic energy, so I'm not talking about thermal energy here, I'm only talking about the energy associated with motion. The translational kinetic energy is 3 halves nRT. Right? Even if you have more thermal energy because a molecule is rotating or vibrating, only 3 of those modes are because of translational motion. So no matter what kind of molecule you have, Ke translational is this. And translational kinetic energy, remember that this is equal to 1/2 mv squared. So we can start to relate how fast the molecules are moving with what the temperature is. So in equilibrium, there's only one temperature here. So you might think that every gas molecule is moving at exactly the same speed. That's not true. Really, it's moving at, there are a whole bunch of speeds. And this is sort of an average speed. This is a special kind of average called the root mean square speed. So because it's related, the name here is related to the fact that there's a v squared. So square the speeds, take the average, take the square root. That's what this average is. And this is the only kind of average speed that we're going to care about in this class. So we're going to derive a quick result, but really you should know the derivation even more than the result. So we're just saying, so you should know why we set these two equal to each other. But if we continue on with this, we can derive that the root mean square speed, so we can cancel out the 2, move the mass over to the other side. Looks like this is nRT over m square root. Oh, I forgot a factor of 3, didn't I? 3 nRT. So what we just wrote down here is this is the total energy right here. But right here we just wrote down, so this is the total energy for all the gas molecules. And right here, we just wrote down, so we have to be careful with the mass right here. So here, this is the kinetic energy of all the gas molecules. So maybe it makes more sense, though, to not talk about all the gas molecules, but maybe one at a time. Okay, so this is all the kinetic energy for all the gas molecules. But now let's just talk about one gas molecule. So let's say that this one is for all of them, and then this is only one molecule. So this is the mass of one molecule now. And then now remember this NR was capital N times K for all the gas molecules. But if we're not talking about all of them, if we're only talking about one, we can just remove that N right there. So for one gas molecule, if this is the mass of one gas molecule, this equation is going to simplify to 3 kT over the mass of one molecule. And this is exactly the result that your book proves. Okay, so this one right here is what you'll see in the book right there. So this is how fast, on average, the gas molecules are zipping around. It's related to the square root of the temperature. Okay, but and the m right there, so this is the speed of one molecule. That m is the mass of just that one molecule or atom. Okay, so that's why they're plugging in. So right here in this example, they're plugging in for nitrogen at room temperature, 500 meters per second, pretty fast. Right, that's over 1,000 miles an hour. So they're zipping around pretty fast, even at room temperature. Okay, so that was the previous section. We used the equipartition theorem here because we were just focusing on translational degrees of freedom. Now there's one other fact I want to mention, and this has to do with section 20.5. So suppose you have two different systems, and this is finally going to let us be able to answer this question right here. Although we can already answer part A, right? So let's hold off though on answering all of it until we mention one fact. So thermal equilibrium occurs when. So one way of thinking of thermal equilibrium, it's when the temperature has settled. So that's certainly true. Temperature has settled. That's a macroscopic way of talking about thermal equilibrium. But since we're focusing on what the molecules are doing on a microscopic scale, we're going to want another way of thinking of this. So what on a microscopic scale, when does thermal equilibrium occur? And the answer to this comes right here. So see this paragraph, how do the systems know when they've reached thermal equilibrium? This is the most important paragraph right here. How do the systems know? Energy transfer continues until the atoms on both sides of the barrier. So like in our example, this is the oxygen and the helium, which they don't have to. There doesn't have to be a barrier between them. They can also mix in. Energy is exchanged until they have the same average translational kinetic energy. So thermal equilibrium occurs when all molecules, even of different types, have the same KE, the average translational kinetic energy. Okay. So I think the best way to understand what that second thing is saying, though, is through an example. And that's exactly why I want to go over this example right here. So 1 mole of O2 and 1 mole of helium are mixed. Okay, which molecule is moving faster? So the speed of the molecules, remember, is governed by this equation right here. So VRMS, so the original problem of the day. So part A. So VRMS we just derived was square root of 3 kT over the mass of one molecule. Remember that right there. So O2 has a bigger mass. So maybe I should write it this way. The mass of one molecule of O2 is bigger than the mass of one molecule of one atom of helium. And so at the same temperature, the one with the bigger mass has the smaller VRMS. And so VRMS for O2 is less than VRMS for He. Now the molar mass of helium is 4 grams per mole, and for O2 it's 32. So the ratio there is 8. And because of this square root, it looks like it's a square root of 8 for relating these two. So you can actually show that VO2, the RMS speed, is equal to VHE over square root of 8. This is by the way, if you wanted to do this quantitatively, just because we know the relative masses. Okay, what about part B? So part B was what fraction of the total energy does the oxygen have? Remember, what fraction of the total thermal energy does the oxygen have? Well, let's break up the total thermal energy into two pieces. So E thermal total is equal to E thermal due to the O2 and plus however thermal energy the helium has. So this, remember our formula, this was F over 2, and this is going to be the degrees of freedom for the O2. F over 2 nRT, number of moles of O, plus, and then I'll just plug in for the helium, it's definitely 3 for the number of degrees of freedom. The number of moles of helium times RT. Now remember, at room temperature, and this problem is talking about 300 Kelvin, so at 300 Kelvin, the number of degrees of freedom for O2 is 5. So 5 halves times 1 mole. I'm just going to say N is 1 mole. It's the same for both of these. So 5 halves nRT plus 3 halves nRT. So the total thermal energy here is going to be 8 halves nRT. So see how 5/8 are due to the oxygen and 3/8 are due to the helium. So 5/8 of the total thermal energy is due to the oxygen. Or in other words, the oxygen contains 5/8 of the total thermal energy, and then 3/8 is for the helium. And this all has to do with the fact that the oxygen is rotating. So notice how the mass of the oxygen has no role here, even though the mass of the oxygen is greater, and that has something to do with how fast it's going. This fact right here, so if I look at this one right here, so the more massive, so this is going to be the same for both the oxygen and the helium. So the oxygen has more mass per molecule, and it's going to be moving slower. And it's exactly in such a way that 1/2 mv squared is the same for both of them. So 1/2 times the mass of the helium times the speed of the helium squared is equal to 1/2 times the mass of the oxygen times the speed of the oxygen squared. And that's the same for both of these because they're in thermal equilibrium. Okay, please ask questions on Piazza, because I know this is one of the toughest sections in all of Physics 2C. Okay, bye.